Hello, in this video we'll learn to define expected value operator for different distributions, continuous type, discrete type and mixed type, and we will apply them for various distributions, and we will have a couple of examples. So, for example, if we have the probability distribution of a random variable, we could define fx of x. We want to see what is expected value of this random variable x. Or if you have probability density function of x, we want to define expected value of x first. Obviously, later on, using the same definition, we extend this definition and obtain other moments. Generally speaking, the expected value or mean or average of a random variable is defined by either of these two integral, whichever you are more comfortable. If you have your probability measure P over a probability space L, F, and P, if you have these probability measures somehow given to you, either by PDF or CDF and so on. So this is using Lebesgue integral. If you haven't had exposure to Lebesgue integral, you can use the Riemannian integral. And we'll have some more examples that will simplify it for you. And obviously, the result of this integral is a real number. So the expected value is a real number, which is called expected value or the average or the mean value of your random variable. One interpretation is that if you repeat this experiment independently enough number of times, and then this random variable is generated following a given distribution with this probability measure or this probability PDF, then the average of your repeated trial is expected to converge to expected value. So this concept is related to the law of large numbers, and then we will learn a little bit about it in chapter 14 or 15, if I'm not mistaken. In this example, we aim to find the expected value of a normal distribution. We assume that X has a normal distribution with mean mu and variance of sigma 2. This sentence means that the PDF fx of x is equal to e to the power of, is a bell-shaped function, minus 1 over twice the variance, sigma 2, and then times x minus mu to the power of 2, and then divided by the square root of 2 pi sigma 2. So this is a distribution. And we want to find the expected value of x. Expected value of x by the definition that we given in the previous slide is integral of the average of x using these probability measure. So when x is any arbitrary real number. So this basically means integral over all possible values that x can take, because we are calculating the expected value of x, and this x could be any real number x from minus infinity to plus infinity, and times this measure of probability, which is this PDF f x of x dx. So this is the general definition that we have to calculate. We have to calculate this integral. So this is the distribution. This normal means that fx of x is equal to that. Sometimes we denote x is distributed normally with mean mu and variance of sigma 2. So this is an abbreviation. So in general case, we have to vary all possible values of x from minus infinity to plus infinity, and then we multiply the value that this x can take on and times the distribution. So this is dp. Obviously, if you multiply the value of x by this is the PDF, you get this integral. How to calculate this integral? In order to calculate this integral, this value of x is equal to x minus mu and then plus mu. I replace this x by this one because I have x minus mu, and then I change the dummy variable. So what I get this expression. So this part I write it separately, and then I will have another integral. So I will get an integral of let's say x minus mu, and then e to the power of minus x minus mu to the power of 2 divided by 2 sigma 2 divided by a square root of this, and then dx, and then plus integral of mu, and then e to the power of minus x minus mu to the power of 2 sigma 2 divided by square root of 2 pi sigma 2 dx, from minus infinity to plus infinity. This integral is 0, obviously, because this function here is odd. Like if you consider it as g of x is equal to g of minus x and then a minus. So because it is odd, its area, if you have an odd function, so if you plot this function, you get something like that. So this area, if you say integral from let's say from alpha to minus alpha to alpha, integral of minus alpha to alpha of g of x d of x, this is equal to 0 because this area is equal to minus of this area, and then they add up to be 0. So the first part is 0, and the second part you can take this mu, so you get equal to 0 plus mu integral of something, and integral of this something, because this is the PDF, the integral of PDF from minus infinity to plus infinity should be equal to 1. So the result will become mu times 1, which is equal to mu. Let us summarize it. So obviously the first part you could change the dummy variable here. So you replace x minus mu by, let's say, x. So the area from minus infinity to plus infinity is not changing, and the integral simplifies, and so on. So you have to follow the steps of this one and find this one. So what we conclude, that if x has a normal distribution of mu and variance of sigma 2, the expected value of mu of my random variable is equal to mu. So mu is not only the center of the distribution, but also it is equal to expected value, the mean of your random variable.